In this list of videos, we're going to show how to use convolutional neural networks for common computer vision tasks like detecting objects. And convolutional neural networks is a type of layer, deep learning layer, that is good for image processing activities. Okay, so for this, we're going to use Keras, which is a deep learning library that depends on TensorFlow. It's an abstraction layer on top of TensorFlow to make the use of deep learning easier. And it's like democratizing the use of deep learning. It has utilities like you can see here, layers, models to create a deep learning architecture from the scratch, but also has a pre-trained neural network models, and also have some data sets and other things that facilitate the use of deep learning. So, okay, for a convolutional neural network, as mentioned before, is good for image processing. You can see it as a type of translation from an image into a category. Like in this case, you're trying to detect a car, and you have the image of a car, and there's the categories of car, truck, van. So you're gonna have in this type of networks a mixture of convolution layers and also pooling layers. The convolution layers are window neighbor processing operations in which the output of the pixel, as you can see here, depends on the neighbor pixels. That is seen easier in here. It's like a sliding window that the output pixel depends on the neighbors. And it's good for detecting local patterns. And then you have the max pooling, which is like a morphology operation that takes the maximum of pixels or something like that. And this is like detecting patterns between patterns. It's like a more global pattern detection. For example, if you want to detect a car, this is like a global pattern in the image that you're detecting. So detecting small patterns locally is not going to be enough. You have to have a combination of both. And this one is good for doing things like detecting a small, like connecting edges, like using something like doing something like an edge detection. And so yeah, the closer that you are from the image, the networks is gonna be image like, and the closer you are from here, it's gonna be more category like. And yeah, so you apply all these layers, and then you have to flatten them. The tensors have to be flattened because you're gonna go to detect categories, and then you go use fully connected neural network. And notice that you use a ReLU for the output of the convolutional neural network. ReLU is basically it's a max function that if you're less than zero, you're gonna be zero, and otherwise it's gonna be a linear function. This seems to be good for convolutional neural networks. And for the output, you're gonna use a softmax, which is like a normalized exponential, and it's gonna look like this. So it's like, I understand that this is for highlighting one of the options, so that you have a one and only one category shown at the end. Okay, so let's go to the network, and for that you create a sequential model. You select the convolutional neural network. The size of the image is going to be from MNIST. This is provided by Keras as well. As Goodfellow mentioned in his book, this can be seen as the Drosophila for deep machine learning. It's a very common way of training neural networks and testing how good your model is. And so the size of those images are that's going to be numbers from 0 to 9, and the size is going to be 28 by 28, and they're going to be grayscale, so you only have one color channel, so it's 28 by 1. And we're going to use the ReLU activation as mentioned before. And another detail about convolutional neural networks is that notice that in times past, in order to detect objects, you use things like Sobel edge detection, morphology operations like open, close, use also Gaussian filters and things like that. All of those image processing operations are neighbor processing operations, and also convolution operation is like a neighbor operation. So you can see the convolution operation, which can also be compared to a matrix multiplication. You can see it as a generalized image processing operation. So when you train the network, you automatically get your image processing filters and pre-processing of the image for free, instead of having to, like in the old days, select edge detection, filtering, and all that. That is done automatically by the convolutional neural network. It detects the features for you, rather than you finding the features manually and painfully through image processing. Okay, so yeah, we're gonna select for the first layer 32 channels. 3 by 3 is the size of the window. Like for example in here, happens to be 3 by 3 as well. And so yeah, and then you have a max pooling layer. And okay, so we have 3 layers of the same. We're gonna run it, and then we're gonna get the summary of the convolutional neural network. You can see here that the image is 28 by 28, but the output of the first layer is 26 by 26. This is because since we're doing a neighbor processing operation, the edges, if you try to do it on the edges, you're gonna be out of bounds of the image. And to avoid going out of bounds, Keras is gonna remove the upper and lower row, the left and right most columns. So that's why you lose 2 elements in each dimension. And to avoid doing that, you could use padding. There's an option for that, but we're not using it. And also max pooling is gonna reduce the size of the image by half each time you run it. So you can see at the end that you have 3 by 3 by 64. Okay, so now we're gonna add the layers for classification. So, so we have an output image, we have to flatten it, and we have a layer for flattening the dimensions. Still we have for another dense layer with 64 channels, again with ReLU. And finally, we have softmax for the output of the neural network, and we have 10 channels. And we have 10 channels because we have to have 10 categories, numbers from 0 to 9, and those are gonna be our numbers. So we're gonna run it. We have the summary, and we have the convolutional layers. We have the flattening layer, which is gonna multiply all these dimensions, and then we have the dense layer and the output layer with the softmax. Okay, now we're gonna get the data set MNIST, this one, and we're gonna load it. And notice that this data set is already prepared for training. We're gonna do supervised learning, in which each image has a corresponding label. In this case, for example, it will be 0, has a 0, this has a 5, this has a 9, and that's gonna be the labels for training. And also we have a separate test set. When you train a neural network, you have to separate some of the data for training and some of the data for validation and testing, because otherwise, if you use all the data for training, you're gonna overfit your model. You have to regulate and validate that model in order to keep it simple enough and general enough to be able to predict data outside of your training data set. Okay, so let's adapt that. We loaded the data, we have to adapt it. We have 60,000 samples, which is a lot relatively. And we adapt the image size, and the images unsigned integer 8, which is from 0 to 255, but neural networks are better suited for values between 0 and 1, so that's why we divide by 255. Then we do another adaptation of the data using the categorical, and then we compile the model. For the optimizer, we use root mean square propagation, and for the loss function, we use categorical cross entropy and train for accuracy. When you train a neural network, what the algorithm is going to do is going to do something like a gradient descent, in which you use a loss function and try to minimize the loss function. And the loss is going to be between the output value and the predicted value. So you're trying to minimize that difference. And the gradient descent is going to compute the gradient, the reverse gradient of your neural network, and try to minimize it. So the algorithm that is used to do that, to train the network, is going to be RMS propagation. So let's compile it. And now to train it, you have a couple of options. Batch size, which is the number of samples per batch, and what that's going to do is going to fit 64 samples before applying before updating the weights of the neural network. So after 64 samples, the algorithm is going to compute the loss using the categorical cross entropy, and it's going to update the weights after that. It's more efficient to do that way. And then you're going to run, after training with all the data, you're going to apply it 5 times, and that's why the epoch is 4. So you're going to go to run through the whole training data and while actualizing the weights. And this is the part that takes the most. For the next, right now I'm showing the example of training for numbers. The next example is going to be for training for detecting cats and dogs. That takes a lot of time, maybe 20 minutes to train one of the neural networks. So this is relatively fast, but still I'm gonna pause it because it takes a lot. You can see that for each epoch, the loss is gonna be less and the accuracy is gonna be higher. I'm gonna pause now. Okay, the neural network finished training, so you can see that it begins with 94% accuracy and ends up with 0.99, which is pretty good, and the loss is quite low. Now, but that's with the training data. Let's see how it does with the test images and the test labels. So we are going to evaluate the model to see how good it is. So we got 99% accuracy and very low loss. So yeah, so we can see the numbers in here, and yeah, this is a simple problem, just detecting text. So that's why we get such a high number accuracy. But also MNIST there's a lot of data in this data set, 60,000. So that also helps in getting this accuracy. Okay, so now we're gonna test the trained model. We have to expand the first dimension, and that's basically adding this unitary dimension at the end so that it can basically fit. So we have the first image. You can see test images. We get the first one and assign it to here. So now we're gonna plot it. So we get number 7, and now we're gonna use the predict method of the model with the first image to see what are the predicted values. And this is each one is the percentage, the probability of the particular digit to be corresponding to the image detected. So this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the highest number is the one that is going to be the detected value. In this case, you can clearly see that the value number 7 has the highest probability. So yeah, so this is like maybe 0.1 or something like that, but it's the highest value. So basically saying that the detected value is 7. Okay, so that's it for this example. So in the next example, we're going to show how to train a convolutional neural network for detecting cats and dogs. First, we're going to do it from the scratch, and then we're going to do it with a pre-trained model. Thank you very much.